Okay, so let's see another example of another situation where we can apply oxidation numbers in conjunction with another characteristic to examine a particular type of chemical reaction. So here we're looking at the oxidation of metals now in aqueous solution. So generally what we're looking at here is whether a metal is able to lose electrons. That is what oxidation is, the loss of electrons. And whether it's able to lose electrons is an indication of its reactivity or activity. Okay, so we're going to talk a little bit more about this. So this is an example here. We have zinc reacting with copper chloride, copper 2 chloride to make zinc chloride and copper. So this is an example of a single displacement a single replacement or substitution reaction where you have a metal replacing an atom or an ion, replacing another atom of another element in a compound. So generally, we saw this before. If I have an element A reacting with a compound BC, A can possibly replace B to make a new combination LAC, and then B is kicked out on its own. All right. So we can look at, in this specific example, we can look at the oxidation number. So zinc here, elemental zinc will have an oxidation number of 0. The copper 2 chloride here, monoatomic ion will have a charge of -1, or I'm sorry, oxidation number of -1. We have 2 of them, so times 2 will give you -2, which means then that the copper should have an oxidation number of +2. On the right side, the zinc with the zinc chloride, again, the Cl here will be a -1. You have 2 of them to give an overall contribution -2. The zinc here has to be +2 to cancel that out. And the copper metal on its own, right, is going to have an oxidation number of 0. That doesn't, for individual or elemental metals in their elemental state will have oxidation numbers of 0. So what's happening here is if we look at what's occurring with the zinc, for instance, zinc goes from 0, oxidation number 0, to +2. So the zinc then is oxidized, right? There's an increase in the oxidation number, which means then that the copper is the thing that has to be reduced, and we can tell because if you look at the oxidation number, copper goes from +2 to 0. Right, so there's a decrease in the oxidation number for copper. So again, we have both happening simultaneously, both oxidation and reduction. In case of the chlorine, right, nothing is happening to the chlorine. Its oxidation number stays at -1, -1. So it's neither oxidized nor reduced. So why is the zinc able to replace or displace the copper in the first place? And could the opposite be true? Why couldn't the copper displace or replace the zinc? Well, the reason there is due to the relative reactivity or the activities of the metals. Okay, so the activity series is simply a list of all the metals, and we also have hydrogen as a reference in there, arranged from top to bottom in the order of decreasing ease of oxidation, right? Or another way of saying that, or in the order of decreasing activity. Okay, so the most active are at the top, least active are at the bottom of the activity series. Okay, so the metals at the top, those are obviously very active. We call those our active metals. The ones at the bottom, the least active one, sometimes they're referred to as the noble metals. And they are not very reactive at all. You probably saw this in a couple of the labs we've done, specifically the chemical reactions lab, or you will do at some point. So the way that we can compare metals on the activity series is any element in the series will be oxidized by the ions of any element that appear below it in the table. Okay, another way of saying that is the element further up, so the higher the element is, in other words, the more active it is, the more it prefers to be oxidized, meaning charged. Okay, that means then that it prefers to lose electrons. So if we go back to our example, where we had the zinc and the copper fluoride, right? Okay, if I compare zinc and copper on my table, there's zinc and there's copper, right? So which is higher up? Which is more active? Well, zinc is higher up on the table. That means I have two things, zinc and copper together. The zinc will prefer to be in the oxidized state, whereas in comparison, copper will prefer to be in the reduced state. And as a result, the zinc is actually able to come in and kick that copper out as copper metal, so it reduces the copper, and as a result, then the copper oxidizes the zinc, goes from Zn0 to Zn with a charge of +2. If you were to do the opposite, if you had copper metal and zinc fluoride, well, the zinc is already in the ZnCl2, right? This is already has a charge and oxidation number of +2. So there's no need for it to be oxidized. It's already oxidized, so we won't see any reaction occurring there. So let's take a look at another example, a couple examples down here. So which of these reactions will occur? So we have cobalt and barium iodide. Okay, so we want to, when you have problems like these, you want to compare the metals that are in the equation. So we have cobalt, CO, we have barium. So we find them on the table. There's barium, and cobalt is underneath barium, right? So barium prefers to be in the oxidized state. Cobalt prefers to be in the reduced state in comparison because the cobalt is less active. Remember, the more active metal wants to be in the oxidized state, right? So is barium already in the oxidized state? Yes, because it's combined with iodide. So it's already oxidized. It oxidizes any further. So nothing will happen, no reactions. We look at tin and copper bromide. Here's the tin, Sn is tin, by the way. The tin is here. We have copper is right underneath it. Okay, so which is more active? Well, the tin is more active. The tin wants to be in the oxidized state. Right now, okay, the tin is in the elemental, have a charge of 0. Right, it wants to now take the place of the copper. It wants to be oxidized instead of the copper. He wants to reduce the copper, in other words. So yes, there will be a reaction here because the tin being higher up, it wants to combine with something, in other words, right? That's the whole point of this. The more active metal wants to combine with something, it doesn't want to be on its own. What about silver and sodium chloride? So silver Ag and Na, so Ag silver, that's this thing, and then sodium, Na. So which is more reactive? Well, obviously the sodium wants to be oxidized, it wants to combine with something. It already is, and the silver can't do anything for reaction here. Okay, so you want to compare your metals to see which one is higher up. That's the one that would want to combine with something, and it will kick something out in order to do that. Okay, so let's take a look now at how we can balance simple redox reactions. So as with any reaction, you want to make sure that they are balanced in terms of the number and types of atoms. But when it comes to redox reactions, there's another thing that we need to consider, and that is the charge, right? So we need to make sure the charges are the same on both sides of the equation. And what that means from oxidation reduction standpoint is that we're going to introduce electrons, help balance charges. Okay, we know how to change coefficients to balance the atoms, ions, etc. Now we're introducing electrons to help balance the charges. So the first thing that we want to do is we want to write out the half reactions for the process. Okay, so in this example, we have chromium and nickel 2+, it gives chromium 3+ and nickel, right? So you're going to separate it, look, compare the things on either side. So I have chromium solid forming Cr3+. So that's an oxidation reaction, which means electrons are lost. How many electrons do I need to lose to go from a charge of 0 to a 3+? I need to lose those 3 electrons. And then the other two things would be the nickel and nickel 2+ and nickel. For the nickel to go from 2+ to a charge of 0, that's a reduction. It has to gain, in this case, 2 electrons. All right. So what we can see now is I need to, when I look at in each of these half equations, half reactions, I have the same number of, let's look at the chromium. So same number of chromiums, one chromium, but the charges now are going to be different, right? So I have, in the second equation, I have one nickel on one side, one nickel on the other side. In my top equation, right, what I see is that there are 3 electrons on one side. On the bottom one, I have 2 electrons on the other side. So obviously, this can't happen because those electrons need to be the same number. So how do we balance out the electrons? Well, you want to get to the lowest common multiple of 3 and 2, which is 6. So in order to get to 6, I need to multiply the top equation, this entire equation, will be multiplied by 2. And in order to get to 6 electrons in the second equation, I'll need to multiply that entire equation by 3. Okay, so we're multiplying the entire thing by a number, which means then the first one here, everything gets multiplied by 2. So I have 2 CRs to form 2 Cr3+. And then I have my 6 electrons. For the nickel equation, the reduction half equation, I have 3 Ni2+ plus 6 electrons to give 3 Ni solids, right? So I'm changing whatever the coefficient is, I'm multiplying it by that number that I decided to add, so to multiply each of them in the first place. So now I have the same number of electrons on either side of this equation. I can go ahead and add these equations together now. Okay, so I have the 6 electrons are going to cancel out. Whatever's left on the left side here, add that together. So I have 3 nickel, 2+ and 2, plus the 2 chromiums solid to give. On the left, I have 2 chromiums now, 3+, and I'll have 3 nickels, 0s. Okay, so if I look at my overall equation, I can confirm 3 nickels on the left, 3 nickels on the right. 2 chromiums on the left, 2 chromiums on the right. If I look at my charge, so the equation is balanced in terms of the types of atoms. If I look at my charges now, on the left side, I have 3 times 2+, that's 6+. If I look on the right side, I have 2 times 3+, that's 6+. There's a 0 and a 0, so those don't affect anything. The equation is balanced in terms of charge, it's balanced in terms of the number of atoms. That's your balanced equation. That is known as the half reaction method for balancing redox reactions. Okay, so the last thing we'll talk about in this section is, I did mention at the beginning that oxidation reduction reactions are sort of an umbrella type reaction that does house or does encompass lots of other types of reactions. And we'll take a look at a few of these now. So combination reactions, right, which are also known as synthesis reactions, these often involve oxidation reduction also. And remember, for a synthesis reaction, we have multiple reactions that combine together to make one type of a product. So in this example, we have nitrogen, elemental nitrogen, oxidation number of 0, combining with elemental hydrogen, oxidation number of 0, to make ammonia. Okay, and in ammonia, the hydrogen again, oxidation number of 1, we have 3 of them. Sometimes you would give an overall contribution of +3, which means the nitrogen then is -3 in this oxidation number in this compound. So what's happening, again, if I compare, the nitrogen goes from 0, oxidation number 0, to -3. Okay, so the nitrogen is undergoing reduction. And again, by default, what that means is the hydrogen is the same that has to undergo oxidation, right? So it goes from 0 to +1. And what we can also say, or it doesn't say it in this question, we can add this in. If the hydrogen is being oxidized, that means the H is the reducing agent. And whatever is being oxidized is acting as a reducing agent. Whatever is being reduced is acting as the oxidizing agent as well. Okay, so combination can involve oxidation reduction. Decomposition can also be a redox reaction, right? And then in decomposition, you have the opposite of a combination. We have one type of a reaction decomposing or breaking down into multiple products. So again, we have sodium hydride. Sodium is always going to be +1. The hydrogen here, because it's combined with a metal, oxidation number of -1, forming elemental sodium, oxidation number 0, elemental hydrogen, oxidation number 0. When sodium goes from +1 to 0, that's a reduction, which means the hydrogen then has to undergo oxidation. It goes from -1 to 0. Okay, so there's an increase in the oxidation number. It has become more positive, even though it's not positive, but it has become more positive. It goes from -1 to 0. So the H minus in the hydride actually is oxidized. Again, if you have oxidation occurring, you must have reduction occurring simultaneously. Disproportionation reaction is another example where we see redox occurring. And this is special because you actually have a situation where one element actually undergoing both oxidation and reduction at the same time. In the case of hydrogen peroxide, this can undergo disproportionation, where hydrogen starts off with an oxidation number of +1. The oxygen here is -1 in the case of the peroxide. This can form, so this would be another example of a decomposition, but in this case, it's disproportionation, which we'll see why in a second. In H2O, hydrogen has an oxidation number of +1. Oxygen is going to be -2. And then we also form oxygen, elemental oxygen, which oxidation number here is 0. So if you look at the hydrogen starts off with oxygen number +1, stays as +1. The oxygen, though, starts off as -1. It becomes -2. It also becomes 0. So the oxygen here undergoes both reduction, and it goes from -1 to 0. It also undergoes oxidation when it goes from -1 to 0. So this is disproportionation, where the element O undergoes both oxidation and reduction in the same reaction. The last type of reaction that also involves reduction oxidation processes, a combustion reaction. Remember, combustion is typically where you have a compound reacting with oxygen to produce carbon dioxide and water. So for instance, if you look at, and we'll just choose a couple of these to illustrate our point. If you take a look at the, let's see here, let's take a look at the oxygen. The oxygen starts off with a chart with the oxidation number of 0. and it becomes oxidation number of -2 on both sides. So that would be an example of a reduction that's occurring, which would suggest that something else has to undergo oxidation. And even though it's not apparent in this example, right, the carbon, both the carbon and the hydrogens are undergoing oxidation. And again, we can see here the carbon, let's see, carbon starts off with a oxidation number of -4. It becomes +4. So that's, very obvious example there of the carbon undergoing its oxidation number increasing, which is an oxidation process with going hand in hand with the reduction of the oxygen in these two products that occur. So combustion is a really good example, and we take advantage of combustion processes all the time to generate energy. It's the prototypical example of reduction oxidation. We can chart it in terms of the oxidation numbers. Obviously, we can see also a little bit more apparently here in this. If I look at my CH4, the carbon, when it becomes CO2, for instance, right, the carbon loses hydrogen, but the carbon also gains oxygen. Remember, back at the beginning, we came up with a table that looked at the differences between oxidation and reduction. Losing hydrogen, that's oxidation. Gaining oxygen, that's oxidation. And guess what? Increase in the oxidation number, that's oxidation as well, right? So you can actually see this occurring in three different perspectives. If you look at the oxygen here the oxygen is by itself. It now has attracted hydrogen, so the oxygen gains hydrogen. That's an example of reduction, right? We can also confirm that because the oxidation number goes from 0 to -2.